Hello students, in this lecture we can discuss various issues regarding classification and prediction, and also we can discuss about classifier accuracy. Data mining is not an easy task as the algorithms used are very complex and data is not always available at one place. It needs to be integrated from various heterogeneous data sources. It has some issues which are discussed under three categories. First category is mining methodology and user interaction issues. Second issue is performance issues, and the third one is diverse data types issues. The diagram describes the major issues under three categories. First, let us discuss the various issues under mining methodology and user interaction. It refers to the following kinds of issues. First, mining different kinds of knowledge in databases. Different users are interested in different kinds of knowledge. It is necessary to cover a broad range of knowledge discovery tasks in data mining. Next, we can see about interactive mining of knowledge at multiple levels of abstraction. The process of data mining needs to be interactive because it allows users to focus the search for patterns, providing and refining data mining requests based on the returned results. And the third issue in the first category is incorporation of background knowledge. The background knowledge can be used to guide the discovery process and to express the discovered pattern. It may be used to express the discovered patterns not only in concise terms, but also at multiple levels of abstraction. The next issue is data mining query language and ad hoc data mining. It allows the user to describe ad hoc mining tasks. It should be integrated with a data warehouse query language and optimized for efficient and flexible data mining. Next, presentation and visualization of data mining results. Once the patterns are discovered, it needs to be expressed in high level languages and visual representations. These representations should be easily understandable. The next issue is handling noisy or incomplete data. This issue is very important in data mining. The data cleaning methods are required to handle the noise and incomplete objects while mining the data regularities. In the absence of data cleaning methods, the accuracy of the discovered patterns will be very poor. Pattern evaluation. The patterns discovered should be interesting because either they represent common knowledge or lack novelty. The second issues is performance issues. It refers to the following kinds of issues. Number 1, efficiency and scalability of data mining algorithms. In order to extract the information from a huge amount of data in databases, data mining algorithm must be efficient and scalable. Next issue is parallel, distributed and incremental mining algorithms. These algorithms play very vital role in data mining. The factors such as the huge size of databases, wide distribution of data and complexity of data mining methods motivate the development of parallel and distributed data mining algorithms. These algorithms divide the data into partitions which is further processed in a parallel fashion. Then the results from the partitions are merged. The incremental algorithms update databases without mining the data again from the scratch. The last category of issues, diverse data types issues. Here, handling of relational and complex types of data. This is the first issue. The database may contain complex data objects, multimedia data objects, spatial data and temporal data. It is not possible for one system to mine all kinds of data. The second issue comes is mining information from heterogeneous databases and global information systems. The data is available at different data sources on LAN or WAN. These data sources may be structured, semi-structured or unstructured. Therefore, mining the knowledge from them adds challenges to data mining. Next, we can discuss about various issues regarding classification and prediction. The issues regarding pre-processing the data of classification and prediction and the criteria for the comparison and evaluation of classification methods are described in this section. Next, we are going to see how to prepare the data for classification and prediction. The following pre-processing steps apply to the data in order to improve the accuracy, efficiency and scalability of the classification or prediction process. The first and foremost step is data cleaning. This refers to the pre-processing of data in order to remove or reduce noise by applying smoothing techniques and the treatment of missing values. Example, by replacing a missing value with the most commonly occurring value for that attribute or with the most probable value based on statistics. Most classification algorithms have some mechanisms for handling noisy or missing data. Data cleaning can help reduce confusion during the learning process. The next important step is relevance analysis. Many of the attributes in the data may be irrelevant to the classification or prediction task. For example, data recording the day of the week on which a bank loan application filed is unlikely to be relevant to the success of the application. Furthermore, other attributes may be redundant. Hence, relevance analysis must be performed on the data with the aim of removing any irrelevant or redundant attributes from the learning process. In machine learning, this step is referred to as feature selection. Including such attributes may otherwise slow down and possibly misleading the learning step. Ideally, the time spent on relevance analysis when added to the time spent on learning from the resulting reduced feature subset should be less than the time that spent on learning from the original set of features. Hence, such analysis can help to improve classification efficiency and scalability. And the next step is data transformation. The data can be generalized to higher level concepts. Concept hierarchies are used for this purpose. This is particularly useful for continuous valued attribute. For example, numeric values for the attribute income generalized to discrete range such as low, medium and high. Similarly, nominal value attributes like street can be generalized to higher level concept like city. Since generalization compresses the original training data, fewer input output operations may be involved during learning process. The data may also be normalized, particularly when neural networks or methods involving distance measurements used in the learning step. Normalization involves scaling all values for a given attribute so that they fall within a specified range such as minus 1.0 to 1.0 or 0.0 to 1.0. In methods that use distance measurements, for example, this would prevent attributes with initially large ranges, say for example income, from outweighing attributes with initially smaller ranges such as binary attributes. Next, we can discuss about comparing various classification methods. Classification and prediction methods can be compared and evaluated according to the following criteria. First criteria used is predictive accuracy. It is the ability of the model to correctly predict the class label of new or previously unseen data. The next criteria is speed. It refers to the computation cost in generating and using the model. Robustness, it is the ability of the model to make correct predictions given noisy data or with missing values. Scalability. It is the ability to construct the model efficiently given a large amount of data. Interoperability. The model provides the level of understanding and insight. Next, we can discuss about classifier accuracy. First, we will see what is classifier. A classifier is a supervised function, nothing but machine learning tool where the learned or target attribute is categorical or it is nominal. It is used after the learning process to classify the new records or data by giving them the best target attributes, which is nothing but prediction. Rows are classified into buckets. For instance, if data has feature X, it goes into bucket 1, if not, it goes into bucket 2. The target attribute can be one of a K class membership. To summarize the results of classifier, a confusion matrix may be used. Here, classification, the learned attribute is categorical or it is called nominal, but in case of regression, the learned attribute is continuous numeric value. The classifier takes test examples and hypothesizes classes for each test example. On every test example, its guess is either right or wrong. You simply measure the number of correct decisions your classifier makes divided by the total number of test examples, and the result is the accuracy of your classifier. Next, we can discuss about accuracy measures in classification. The accuracy of a classifier is the probability of correctly predicting the class of an unlabeled instance, and it can be estimated in various ways. Let us assume for simplicity to have a 2-class problem. As an example, consider the case of a diagnostic test to discriminate between subjects affected by the disease, it is nothing but patients, and healthy subject, which is nothing but controls. Accuracy measures for binary classification can be described in terms of 4 values: TP or true positives, the number of correctly classified patients; TN or true negatives, the number of correctly classified controls; FP or false positives, the number of controls classified as patients; Fn or false negatives, the number of patients classified as controls. The sum of TP, Tn, Fp and Fn equals n, which is nothing but the number of instances to classify. These values can be arranged in a 2×2 matrix called contingency matrix, where we have the actual classes P and C on the rows and the predicted classes P cap and C cap on the columns. The classifier sensitivity, also known as recall, is defined as the proportion of true positives on the total number of positive instances. Sensitivity equal to TP divided by TP plus Fn. In the above example, it is the number of correctly diagnosed patients on the total number of subjects affected by the disease. The classifier specificity, also referred to as precision, is defined as the proportion of the true positives on the total number of instances identified as positive. Specificity equal to TP divided by TP plus Fp. In the example, it corresponds to the number of correctly diagnosed patients among all positive diagnoses. In the above example, it corresponds to the number of correctly diagnosed patients among all the positive diagnoses. A low sensitivity corresponds to a high number of false negatives, while a low specificity indicates the presence of many false positive. According to the context, high rates of false negative or false positive predictions might have different implications. Consider failing to diagnose a sick subject, which is nothing but false negative, versus assigning a treatment to a healthy subject, which is nothing but false positive. The simplest way to estimate accuracy is to compute the percentage of correctly classified patients positive instances. PA positive equal to 100 into TP divided by TP plus Fn, which is complemented by the percentage of correctly classified controls, which is nothing but negative instances. Hence, PA negative equal to 100 into Tn divided by Tn plus Fp. The figure shows the trade-off between specificity and sensitivity. In the first panel A, the sensitivity for the red class is highest since all red dots have been assigned to the same class, but the specificity is low since there are many false positives, which is represented as blue dots in the red class. In the second panel B, the specificity for the red class is highest since all points assigned to that class are red, but sensitivity is low for the presence of many false negatives, red dots in the blue class. In the last panel C, there is a balance between sensitivity and specificity. Taking into account all the correctly classified instances, accuracy can be computed as PA equal to 100 into TP plus Tn divided by TP plus Dn plus Fb plus Fn. Another option is to average PA positive and PA negative to obtain the average percentage accuracy on both classes as follows: PA average equal to PA positive plus PA negative divided by 2. Here F measure or F score or F1 score has been introduced to balance between sensitivity and specificity. It is defined as the harmonic mean of the two scores multiplied by 2 to obtain a score of 1 when both sensitivity and specificity equal to 1. Here F equal to 2 into 1 by sensitivity plus 1 by specificity. If we simplify this equation, we get 2 into specificity into sensitivity divided by specificity plus sensitivity. Care must be taken when selecting an accuracy measure in presence of unbalanced classes. Following again the above example, consider the case of data set where 90% of the subjects are sick subjects and the remaining 10% consist of healthy controls. Taking into account only the percentage of correctly classified instances, a model which assigns every subject to the patient's class would attain an accuracy of 90%. In the same case, the F measure would be equal to 0.95, while the average percentage accuracy on both classes PA average would yield a more informative score of 45%. When working with more than two classes, say for example M, the resulting contingency matrix X equal to Xij. It is a M cross M matrix where each entry Xij is the number of instances belonging to class I that have been assigned to class J for I comma j equal to 1 to M. The sensitivity for class I can then be computed as using the formula sensitivity of I equal to 100 into Xii divided by Ni, where Ni is the number of instances in class I. Similarly, the specificity for class I is calculated using the formula specificity of I equal to 100 into Xii divided by Pi, where Pi is the total number of instances predicted to be in class I. The percentage of all correct predictions corresponds to PA equal to 100 into summation of I Xii divided by N. To conclude, there is a huge amount of data available in the information industry. This data is of no use until it is converted into useful information. It is necessary to analyze this huge amount of data and extract useful information from it. Extraction of information is not only the process we need to perform. Data mining also involves other processes such as data cleaning, data integration, data transformation, data mining, pattern evaluation and data presentation. Once all these processes are over, we would be able to use this information in many applications such as fraud detection, market analysis, production control and science exploration. Thank you.